This is video 21.3. We will be looking at the force between two wires. The question: a current carrying wire is juxtaposed with a current carrying loop as shown below. Given the dimensions provided in the diagram, what is the magnitude and direction of the net force on the loop? Step 1 will be to find the magnetic field due to the wire. Now the magnetic field of a long straight wire circulates around it in a direction given by the right-hand rule. Taking the thumb of our right hand, pointing it along the direction of the current, our fingers circulate in the direction of the magnetic field, so that it's coming out of the page above the wire and going back into the page below the wire. The magnitude of the magnetic field is given by this formula, where I is the current, R is the distance from the wire, and mu naught is the permeability of free space, and it has this value. The question asks for us to find the net force acting on the loop of wire due to the magnetic field of the long straight wire. Now the magnetic field acts on each part of the loop. However, the two sections of the loop which have just been highlighted in light blue give a total contribution to the net force of 0. This is because they have the same length, they're at the same distance from the wire, but the current is flowing in opposite directions. On the right side it's flowing down, on the left side it's flowing up, so the two forces cancel each other out. However, the forces due to the sections which are parallel to the long wire do not cancel out. This is because one of them is closer and the other is far away, so they partially cancel, but they don't completely cancel. So first we'll find the magnetic field due to the portion of the loop which is 2 centimeters away, which here I call B sub 2. The current of the long wire is 3 amps and the distance is 2 centimeters or 0.02. Putting this all together, we have this value for the magnetic field. And it's into the page. For the magnetic field 6 centimeters away, which is the distance for the opposite end of the wire, which has just now been highlighted, we have the same formula, except this time it's 3 times farther away. So the distance is 0.06 and the magnetic field is 1/3 of what it was. And it's also into the page, as indicated by the red X's. Now we're ready to find the force on the loop of wire. The force on a wire, as discussed in the previous video, is given by ILB sine theta. And here, the current represents the current in the loop, not the current in the long straight wire. The current in the loop is also 3 amps. The length of that section of the loop, which is 2 centimeters away, is 0.1 meters, and the magnetic field at that distance away we just found. And this gives us our result for the force acting on that portion of the wire. We use the right-hand rule to find the direction of the force. Putting our fingers to the right along the direction of the current, curling into the page, our thumb points upward, so the force is towards the straight wire. Now we repeat for the section which is farther away from the long straight wire. Everything is the same except we plug in the other magnetic field. And we get the force which is 1/3 of the other force. However, we'll find it's in the opposite direction using the right-hand rule. If we put our fingers of our right hand to the left, curl into the page, we find that the force is away from the straight wire, downwards. So the net force is the sum of the forces. Keeping in mind that they're in opposite directions, one has a different sign. And we find this value for the net force acting on the loop of wire. And the direction of the force is towards the straight wire. And that concludes video 21.3. Check out PhysicsX on the App Stores. This revolutionary physics app for smartphones and tablets contains over 100 videos and 500 multiple choice questions designed by education experts. It's been proven to improve scores for intro college physics, AP physics, MCAT physics, and more. Just look for the blue icon.